Thanks very much, Chris, Ben, Dean. It's always an honor to be the first speaker in a conference like this, but it's especially an honor to be the first speaker on the first ever conference on aerial robotics and drones. It's a real pleasure to be here, and I'm really thankful for this opportunity to share with you some of the work that my students and I are doing on unmanned aerial vehicles. As you know, the industry is experiencing exponential growth. If you look at this curve, this chart, it looks pretty ordinary, but just pay attention to the y-axis, which is logarithmic. For all us nerds out there, that makes sense. The number of UAVs worldwide is increasing dramatically. It's a $10 billion industry. In the US alone, there's about 7,500 UAVs. There's over 75 countries that are investing in UAV technology. But the excitement really comes from all the civilian applications that we're going to be talking about at this conference, and particularly all the do-it-yourselfers that are out there, millions of them all around the world. There are startups, exciting startups being formed in this space every day. Matternet, interested in logistics and transportation. Halo Drop, coordinating FEMA operations with small UAVs. 3D robotics, of course, with Chris Anderson. SKYCATCH, interested in monitoring construction sites and precision farming, aerial photography. A company that we've been working with is a spin-off from our lab, Identified Technologies, where they're using robots with ground-penetrating radar to detect IEDs, to enable convoys to progress more quickly through fields that might have IEDs buried. KML Robotics, and this application we're looking at has to do with inspection, the insides of penstocks of hydroelectric dams. And you can see this image here taken from a small quadrotor, which essentially shows a corroded spot in this penstock. So there are lots of UAVs that we read about in the press. Most of them have to do with military UAVs. These are the big, large UAVs on the right side. And of course, these UAVs, we have to remember, are controlled by flight crew, and this is just two people in New Mexico Air Base that are driving it. One of them is actually driving, joysticking this UAV. The other one is looking at the sensors feed from the UAVs. But you have to remember there's a flight crew, oftentimes 10 to 20 people behind each of these UAVs, and they're really remotely piloted aircrafts, as General Norton Schwartz said. And in fact, he objects to the use of the word drones, as I do. What we want to do really is build UAVs that are autonomous, which are not really drones, aircrafts that can think for themselves and do the right thing. Our interests are not in these big UAVs. We build UAVs that are really small, at most a meter in diameter, and capable of navigating rooms like this, in hallways. The smallest one, we now 3D print these, and it takes about 2 hours to print one of these. And it's smaller than the size of my palm. I'll show you some of these videos as we go through the presentation. The best design, if you want to build lots and lots of these, and we're interested in building swarms of these, is the quadrotor. There's nothing simpler than that, a rigid structure with motors and 4 propellers, and a microcontroller that controls the speeds. Of course, you all know this. One thing I would emphasize is that size does matter. If you make things smaller, if you shrink the size, and if you take this length r and you look at the physics of what happens if you take r and reduce it to r divided by 2, you'll find that the mass decreases substantially, the inertia decreases substantially, even the thrust decreases. But the key point is that if you look at the acceleration of the UAV, it actually increases. So if you take r divided by 2, the acceleration doubles. The angular acceleration actually quadruples. So you can make robots that move really quickly, as this really small prototype and, that you can see in this video. On the top, you see the robot able to stabilize pretty quickly. Again, if you have very low inertia, you have a lot of control, and you're able to recover from all kinds of configurations. In the bottom, you see the UAV essentially performing these double flips, and it can do it at fractions of a second, reaching speeds of about 2,000 degrees per second. So we're interested in making these small UAVs, particularly for search and rescue. So this is a picture taken from an experiment we did shortly after the earthquake in Japan, in Sendai, and I'll talk more about this going forward. Obviously, security applications are big. So here you see a UAV performing autonomous patrolling operations in a warehouse-type complex. And with a simple camera, you can actually detect features on the ground. You can track cars, you can track people. So if you see that white Ford Bronco, you can tail it. So these kinds of things are actually very, very feasible. And this is something we're doing with Keynote Robotics. We're really interested in operations and first response. So the first response, the challenge is you have to enter buildings like this from the outside, so you have to operate indoors and outdoors. There is no GPS indoors. And you want these robots to be really small and maneuverable in tight spaces, go through windows, doors, and you want them to be really fast. Usually first response operations have to be done in seconds or at most minutes. And so you want these robots to respond really quickly to human commands. Lastly, we want these robots to operate in teams. If you have small robots, chances are that individual robots may not be able to perform all the tasks that you need. So you really want a lot of these to collaborate to perform the tasks. So these are the things we're trying to look at in our lab. So I want to give you a hint of some of the technology challenges that we work on. Maybe spend 5 minutes in each area. So the first thing that I want to talk about is how we think about the dynamics of these little vehicles and how we try to model them and how we get them to go really quickly through complex environments. So here's just a rough schematic of the control loops that we try to build. You'll see 3 sets of feedback loops. The innermost loop feeds back the orientation of the robot and the angular velocity at about 1,000 times a second, so the order of 1,000 hertz. And it's vital to get this right, because what you really want to do is for the robot to be able to recover from whatever configuration it's in. So this is the attitude controller that is on board in this picture. The intermediate loop closes the loop around the position variable. So you sense where you are in the environment, how quickly you're traveling, what's your velocity, and the position controller tries to follow the trajectory that's then specified by the outermost loop, which is the planner, which basically says if I want to get from here to there, if there are obstacles in the environment, what's the best trajectory to follow? And that's being done at the outermost level, and that's being done 10 times a second. So you have control loops at 100 hertz, 1,000 hertz, 100 hertz, and then 10 hertz. And in this particular picture, you'll see that we actually use some of the computation from laptops that are off-board, and the sensing is obtained by motion capture cameras that are sensing position and velocity 100 times a second. This may not all be feasible but in the outside world, but this is where we do our development. This is where we finesse, we develop algorithms, we test them, we evaluate them, and so on. I want to show you a couple of video clips that illustrate the agility of our robots. The first one is basically showing how our robot goes from point A to point B through an intermediate point C. And you'll see the really large roll and pitch angles that the robot has to automatically figure out how to execute this. And it pitches forward and then it rolls to the side to make this tight turn in a fairly small room. And we call these trajectories minimum snap trajectories because these robots are actually trying to optimize a dynamic variable, which is called snap, which has to do with the 4th derivative of position. So once you know how to do that, you can also go through obstacles. So here these obstacles are represented as hoops. The robot knows where the hoops are, and it's basically trying to figure out what minimum snap trajectory will carry it through these hoops. And again, everything in this environment is completely known. The motion capture cameras on top are telling the robot where everything is with split-second timing. And here you see the hoop being thrown into the air. Well, the robot knows the hoop is in the air, and it figures out how to go through the hoop. And again, if you have these loops carefully tuned, carefully designed, then you can actually do these split-second precision maneuvers quite efficiently. So this is key to get the robots to perform in an agile fashion in 3-dimensional environments. I want to go to the next challenge, which is I showed you all these cameras. How do I get rid of these cameras and make these robots truly autonomous? In other words, how do I get the robot to determine what its state is, estimate its state? State meaning position, velocity, orientation, and so on. So again, in this picture, what I want to do is get rid of the motion capture cameras and get rid of off-board computers. So the key idea here goes back at least 3 years. We took a slightly bigger quadrotor and put on it a Hokuyu laser scanner. So this laser scanner is able to send out beams over a 270-degree field of view, and it's able to map obstacles in the environment. And that is key in order for the robot to figure out where it is. In order to explain this technical idea, let me show you a cartoon. So in this cartoon, you see this robot with 3 pillars. The robot does not know where it is, neither does it know where the 3 pillars are. But if it's equipped with this laser scanner, it can measure the range to these 3 pillars. So it can measure these variables D1, D2, D3. Now imagine a robot takes a small step. So it doesn't know how far it's moved, but it has some idea of how far it's moved from onboard sensors, the accelerometers and the gyros. So it has some measure of delta x. When it goes to this new position, it's able to, again, measure with its laser range finder, get these 3 additional pieces of information. These distances, D1, D2, D3, are different from the original distances. So it has some estimates of the 3 early measured distances, and now the 3 current measured distances, and it knows roughly what delta x is. So now the key question is, can you figure out where the pillars are and how far you've moved? Well, if you write down a few equations, and this is just geometry, trigonometry, you should be able to convince yourself that you can, in fact, solve for these 8 variables armed with the pieces of information that you measure from the sensors. Of course, life is a little more complicated because the measurements that you make are noisy, and to solve for the best estimates is oftentimes hard, and plus you have to do it in real time. But this is the key idea behind what is called simultaneous localization and mapping, where you're localizing yourself, measuring delta x, and you're also mapping where the pillars are. And in the robotics community, of course, we use this cool acronym SLAM. So when you see a problem like this, we slam it, right? But of course, we have to do it in real time. As you see in this vehicle that's taking off outside a building, what the robot sees is on the top right window, and the video on the bottom right tells you what the robot is actually doing. Its internal representation is on the left side. So on the left side, you will see it's measuring all the possible pillars, if you will, and it's actually mapping these pillars. And these pillars, quote unquote, are color-coded. You will see that the blue colors, the cool colors, represent the ground floor, and as the colors get hotter and hotter, you're going up to all the way to the 4th floor. So it's able to build a map as it moves, and the human operator is simply able to click on this interface on the left when he's outside the building and ask the robot where to go to in this map. And then the robot's able to plan an obstacle-free path. And in the process, the robot continues building up this map so that now you're getting the same kinds of 100 hertz update that you did earlier from the motion capture cameras, but now you're getting it from the lasers and the onboard computer. And of course, you can also use vision in the process, but this is the simplest algorithm that you can think of. So this was our first solution to the problem of how do I get rid of the motion capture cameras. Of course, the big problem is you build something like this, and I've been talking to you about building small vehicles, agile vehicles. You're going in the wrong direction. You want to put on a laser scanner, well, you just made it a little heavier, which means you needed to have bigger motors, bigger props. Well, that meant you needed bigger batteries, which in turn meant that you needed bigger motors again. So you're scaling in the wrong direction, and if you think about it, this vehicle consumes 400 watts of power. That's like 5 light bulbs, right? So this is a lot of power. How do you scale things down? Well, we started thinking about how we could build solutions which are similar, but using just cameras. So this is what I call my flying iPhone configuration. So if you look at this, it has 2 cameras, it has an IMU, it has a processor that's actually much better than the processor on this robot. But that sensor package is all you really need to reason about 3-dimensional environment to figure out where you are in that environment 100 times a second. So the key to this is, again, looking at features in the environment or pillars and trying to estimate your distance to those pillars while you move. So this video illustrates this. The only sensors being used here are the 2 cameras and an onboard IMU. On the top left, you see its map. Now, this map doesn't look fancy like the earlier one I showed you, but essentially those dots that appear on the screen are telling the robot what features it's locking onto and where it is relative to the features. And on the bottom right, you actually see the robot executing 3 to 4 meters per second maneuvers at roll and pitch angles of about 40 degrees. So it's able to estimate its state relative to the environment with all the computation being done on board. And what I'm going to show you next is a montage of video clips that use this technology. And so you'll see on the top left, the robot doing a 4 meters per second dash, which I think is the fastest indoor maneuver accomplished thus far by an autonomous vehicle without external cameras, without external computers. This is about two times walking speed. And again, it's triangulating off of features that it sees in the environment. On the top right, you see a similar video, but now this is outdoors. And you have to remember, in outdoors, when you are on top of foliage and you have this downwash from the rotors, everything is shaking, right? It's being blown around by the rotors. And yet the robot is able to triangulate from features that it sees that are consistent from image to image. On the bottom left, you see the ability to do three-dimensional navigation. And again, this is at modest speeds, 1.5 to 2 meters per second. And then on the bottom right, we're now building 3D maps based, again, only on the two cameras. And again, you can start indoors, and then you can exit outdoors, and you can build this really long map now based on visual features. Of course, this map is not as clean as the map you saw earlier, but to a first responder, this kind of map may provide valuable information about what's inside the building. And so with a sensor package, that's 1/5 of the earlier one that you saw. So this consumes about 120 watts of power, and it's about 740 grams in weight. And then finally, this is our most capable robot that we've built to date. And you see on this robot a GPS receiver, 2 cameras, and the laser. So this has the best of all worlds. And I just want to show you the ability of this robot to navigate really complex environments in a minute. So you'll see a 1-minute video clip of this robot being operated through an indoor-outdoor environment in a warehouse-type setting. And you will see that as the video executes, you will see the robot estimating its error in localization. So as the robot moves, you'll see an ellipse that shows how big the errors are. In reality, that ellipse is 100 times bigger than the actual ellipse just for visualization. But you'll see that the robot is now able to navigate this complex environment and have a very good sense of how well it's estimating what its location is. So again, on the top left, on the left side, you see the robot wandering around in this environment. And periodically, we slow down the video to show you what exactly is happening. At any given time, the robot may not be able to use its vision, laser, and GPS. So if you're obviously close to buildings, GPS drops out. If you're in wide open spaces, the laser is not going to give you any information. And likewise, if the camera is looking at a glass wall, it might not see any features of interest. But what you see here is that the robot's navigating roughly a half-kilometer course. And it's doing this at about between 1 meter to 2 meters per second. You'll see it enter buildings, exit buildings. So here it is entering a building on the bottom right. And this is at normal speeds. And you'll see the human operator being able to interact with the screen that's roughly similar to the screen on the left side. So this is a bigger package, but we now have, with this package, the ability to navigate without actually relying on GPS. In fact, the only reason we need GPS is because if you have a map of the environment from Google Maps or what have you, that's registered with GPS. So the only time we need GPS is so that we can take our internal representation that we get with vision and with lasers and map it to the representation that we want to see for our situational awareness as first responders. One big challenge in all of this is obviously power. If you've had a mobile computing device, and who hasn't, you know that power is a big issue. This chart shows all the lithium polymer chemistries that we have available to us. So on the x-axis is the specific energy, the amount of energy you can carry per unit weight. On the y-axis, you have specific power, the amount of power you can source per unit weight. And you see this band, and this was about a year ago, and this was all possible lithium polymer chemistries that we could get at that time. Quad rotors, if you want to build quad rotors for an endurance about 10 to 20 minutes, they need roughly 200 watts per kilo. So that's a lot. Plus, with the limitations, the band that we have with our batteries, we can't fly for too long. That's why the 10 to 20 minutes. To give you some sense of what these numbers mean, here's a cross-section of adipose tissue, fat, that some of us have more than others. It's way off scale here, right? Several orders of magnitude over on this side. How much power do we consume as human beings? Well, let's look at Usain Bolt. In a 10-second dash, he consumes only about 20 watts per kilo. Our robots consume an order of magnitude more. So I have another number for Lance Armstrong, and with or without steroids, he's still burning about 6 watts per kilo. That's pretty efficient for 20 minutes, full speed ahead. So our robots are energy hungry, they're also power hungry. And there is no free lunch here. The only thing you can do is what we all do when we have too much fat, we try to lose weight. And so the best thing you can do is hack away at the denominator and try to build lighter solutions. And this is why it's so important to come up with solutions like this, the flying iPhone configuration, or if you're a Samsung person, the flying whatever, Galaxy S4. But that's the configuration that's most likely to work. And here we have the advantage that consumer electronics is coming up, the industry is coming up with solutions that we can now leverage into robotics technology. And that's what's making this possible. So lastly, I want to talk a little bit about the work we're doing with swarms. And again, a lot of this is motivated by what you see in nature. So here, this picture shows about 500,000 starlings off the coast of Denmark, forming these incredible formations. And the thing you have to remember with these birds as they fly is each bird is acting independently. Nobody's telling them to form these incredibly complex three-dimensional shapes. Second, each bird only needs local information. It's only looking at its neighbors. It's not like it has these amazing sensors that allow it to see all the way to the edge of the formation. It's only looking at its neighbors. Lastly, there's this notion of anonymity. These birds really don't care who they're flying next to, right? So there's no notion of identity here. It's not like the swarm is going to work this way only if bird A flies next to bird B. So these are sort of three organizing principles that allow a flock of birds, a swarm of insects, or large populations to form and function without having direct control of everybody, which is impossible computationally and also practically from a communication standpoint. So we've been trying to see how we can develop algorithms that leverage these basic organizing principles. And I want to show you some work where this is just a small group of robots, but you'll see that we're able to control both their shape and the overall motion. The robots start off in a rectangular formation, they change to the circular formation, and you'll see the circle now flatten into a straight line soon, and then into an ellipse, and then back into a rectangle. All of this happens with some high-level commands where the operator is only commanding the shape and the overall motion. So the operator, in fact, doesn't know how many robots are in the formation. He certainly doesn't care about who's where. But these kinds of maneuvers are being performed automatically with robots just being aware of who their neighbors are. A slightly bigger formation, and this time this is 20 robots, but now the robots are reacting to things that they know exist in the environment. So to form these formations, you can make them 3 dimensions, flatten them out, and you'll see them, again, spread into formations that are specified without telling every robot what to do. And here you see these robots reacting to features in the environment like this doorway, and they're able to flatten these formations and then spread out again once they cross this obstacle. And this is just a cool video that shows the split-second timing that you get. They're executing a figure-8 maneuver, and you'll see these robots actually crossing each other, wingtip to wingtip, if you will, or propeller tip to propeller tip. So what can you do with these? So one application we really looked at is logistics and transportation, carrying packages, and also doing assembly. So here these robots are assembling Lego-like blocks, truss-like elements. They have magnetic fasteners, which makes the assembly easy. But essentially what they're given is the equivalent of a Lego booklet that tells you what goes where. And then the robots figure out who picks up what part from where and assembles it in what position. And again, the assembly is trivialized because they are magnetic snap-fit fasteners. But this just shows the equivalent of a Lego booklet with 3 different designs, and the robots quickly going through these designs. So this is one thing that you could do when you have lots of robots. You can imagine performing tasks that require transportation, logistics, assembly, etc. And you can imagine lots of robots doing this very quickly. Another thing you could imagine doing, and this is something we're very excited about, so you'll see here a collaboration between our university and Tohoku University. The robot that has got tracks is something that's built by Tohoku University. Our robot is riding on top of that. Actually, it's hitching a ride. It can actually fly up the stairs, but you know, the battery, the power problem, our robots are programmed to be lazy, so they hitch a ride whenever possible. But when the ground robot gets stuck, as they do in front of this collapsed doorway, the aerial robot is released. It takes off, and you can see on the bottom right, it's building this map. And it's just a matter of figuring out what the ground robot knows and what the aerial robot knows, and then stitching these maps together so you have a complete 3-dimensional model of what the environment looks like. So you could do this in fairly unstructured environments, and here you'll see, again, the team, the tandem of a ground robot and an aerial robot mapping a fairly complex environment and building maps like you see here. So this is the 7th, 8th, and 9th story of a building that was partially collapsed after the earthquake in March 2011. So this is where I see a lot of the applications. So let me just conclude. In my mind, aerial robots have lots of really interesting applications, but the one that I think has potentially the maximum impact is really by using them for first response, for emergency response, for disaster recovery. So this is a poster from an old Warner Brothers movie. Most of you are probably too young to remember this movie, but don't worry, the movie was terrible. But everything about this poster is true. The swarm is coming. I think we have the potential to take these autonomous robots and create lots and lots of them with technologies like 3D printing. The cost to make them is not significant. The barrier to entry, because of people like you, has become quite low. And clearly, if you put lots of these together, the size is immeasurable, the power is limitless. So at a future conference, you'll have DARC focusing on swarms. Its enemy is man. Even that part is true. Well, maybe I would say its enemy is human. I think it's up to us to sort of embrace this technology and figure out what to do with it. And certainly there are many applications that can benefit from this. And the key thing that's limiting us is really our imagination and our pursuits. I know that this conference is more about things other than technology. It's also about policy. It's about privacy issues and so on. And we have a lot of demonstrators outside our lab. My name is always stuck on one poster or the other. And I get letters like this, which says, is this what we should be doing, building robots that kill people? We really don't do that. I mean, our robots are small and they're fairly benign. And I think the one thing we really need to do together as a community is try to engage the world in discussions on what the benefits of this technology are and how we can really change the way a lot of things are done. For example, first response without putting human lives in danger. And conferences like these are very important, I think. And I'd like the audio to be turned up a little bit because I want to share with you a video clip from the Colbert Report.
For years, I have been warning about the threats of robots rising up against their human masters. Well, now scientists have reached a new milestone in our enslavement. Flying robots that can autonomously assemble magnetic rods into simple cube-like towers. There's no remote control here, folks. These buzzbots have a hive mind of their own, and apparently the first step to enslaving us is building dorm room shelves. Which brings me to threat number 2, flying robot drones. Folks, today they're constructing a 3-foot tower. Tomorrow, it's a sprawling prison for 3-foot prisoners. Provided they can build it before their batteries run out, and it can't be too windy. And even if they don't enslave us, they will crush us at Jenga. Vigilance!
So thank you very much.